Hi, welcome back. This is Unit D still, and Chapter 1 and Lesson 1.3, Harvesting Chemical Energy. So the big thing in this lesson that we're going to be looking at, and I'm going to spend the most time, is Hess's law to figure out how much heat or energy is released from combustion. If you want to read more, there are your textbook pages. All right, so we know there's got to be a lot of energy in fossil fuels, otherwise we wouldn't burn them. And remember, burning is the same thing as combustion. So when we burn a fossil fuel, like this is an example of methane burning with oxygen, always combustion with oxygen, we always get carbon dioxide and water. How much always depends on what you're burning. And we'll get into that balancing formulas. If you ever forget the combustion formula, the description of combustion formula is actually on page 9 of your data booklet. Always remember, this is key, combustion is exothermic reaction. That means energy is always released when we burn something. It has to be released. So we've already been through balancing combustion reactions back in Unit B, so I'm not going to spend time on that right now, but this is an excellent video. It's actually made for Science 30 students, and it's going to give you how to balance these 4 different combustion reactions. So make sure you review that and you understand that very clearly before you move on to the next section. So again, this is a little bit of review from Unit B when we were doing, we were looking at acid rain and different effects of combustion. So when we burn fossil fuels, you need to remember that you're releasing carbon dioxide, which contributes to climate change through the greenhouse effect. Okay, so it traps the thermal energy into Earth. Okay, so the atmosphere traps all that thermal energy. That's the greenhouse effect. So the more CO2 we release, the more energy is trapped in Earth's atmosphere, causing increasing global temperatures, which in turn gives us sporadic weather patterns or climate change. Okay. Some of the effects that we're seeing are glaciers are melting, the vegetation is changing, and we are seeing species extinctions happening currently. So where is the CO2 coming from? As we've been looking at in this unit, a lot of the CO2 is coming from the burning of fossil fuels since we started burning fossil fuels. Whether it's for electricity or for transportation or for heat in our homes, we are burning fossil fuels for a lot of different energy purposes. Also, methane that's leaking and getting into the atmosphere is also a cause of climate change and greenhouse effect. So that's where we have to be careful if we're going to move to natural gas, that we're not releasing natural gas into the atmosphere. Not only is it poisonous, but it also contributes greatly to the greenhouse effect. Methane is also from decomposing waste. So if we have a lot of waste, we get more decomposition, we get more methane. Cattle farming, toots. And as I mentioned already, in the production of oil and gas, especially natural gas, it's released there. Okay, so some of the solutions are listed here to help reduce the amount of carbon dioxide that's being released, or ways to mitigate it. So if you plant trees, those trees absorb the carbon dioxide, so they capture it back in as they grow. We've also there's some technologies out there where they're storing the carbon that's being released. Instead of releasing the carbon, they're capturing it and storing it underground. And then we'll look at some of these in the next chapter about alternative energy sources. So moving to some different alternative energy sources. All right. So the main piece to this lesson that we want to do is looking at how much energy is actually released or absorbed during a chemical reaction. And when we're talking about energy released in a reaction, we're talking about heats of reactions or enthalpies. And you'll see this symbol, delta H. H represents the enthalpy or the heat released, and this little r is for the reaction. Oop, that's a little r. So exothermic reactions, we know release energy that we can use and capture and create electricity with, or we can use that energy that's been released to heat our home. And then endothermic reactions, they absorb energy from the environment. So these are not great reactions. We don't want those ones if we're trying to actually create energy for our usage. Okay, so the heat of reaction. To calculate the heat of release during combustion, we are going to use Hess's law, okay? Along with the standard heats of formation, which are in a data table on page 5 of your data booklet. Huge data table. This is just the first 3 lines, but there's like probably about 20 different compounds in that data table. And these give you the heats of formation. So how much energy went into forming these compounds, basically. Here's a key piece of information you need to know, because if you're starting to look for elements on this chart, you will not find them. So all elements have a heat of formation of 0. So if we're talking about oxygen, that is an element. It's not combined with any other elements. So it's going to have a heat of formation that looks like this, delta H, and then a little f for formation. It's going to be equal to 0 for oxygen. Okay. If you have a compound, then you just look it up in the chart. If you have an element, you know it's going to be 0. Okay, let's put this into action. First, we have to take a peek at what this formula looks like, and this is the formula. This is also on page 5 of your data booklet. You do not need to memorize this formula, but you do need to memorize how to use this formula, or know how to use this formula, and what all the pieces mean. Okay, so here, this is what we're trying to solve for when we're dealing with this Hess's law. We are looking for the energy change of a reaction, and that's what this symbol represents. So the change in enthalpy or energy, you can think for the reaction. That little r means for the reaction. So what we're going to do is we're going to look at all the products first. Okay, and this thing, weird looking thing, is telling us that we're going to take the sum of all the products energy enthalpies of formation, so the amount of energy in their formation, times by however many moles of each of those products we have. We're going to take them all first, and then we're going to subtract all the enthalpies of reactions times the number of moles for all the reactants. Okay, so let's just see this in action. This equation looks kind of weird and scary because there's a lot of intimidating symbols in it, but once you start using it, not so bad. It follows a nice similar format. Let's follow the format here. Okay, so here's an example of the combustion of glucose. Okay, so we want to calculate the heat of combustion. So basically how much heat is released when we burn glucose. So when we burn glucose in combustion. Okay, so combustion reactions, if you did all that practice reviewing of balancing combustion reactions, you will remember, hopefully you go back and did that, that every combustion reaction is going to, the molecules are going to combine with oxygen gas. Okay, so they're going to react with oxygen gas in all combustion. Okay, and we're always going to form carbon dioxide and, oh, that's a gas, and water vapor. And we're always going to assume water vapor or gas because we're talking about combustion. That means heat, that means hot, so the water is going to be a gas. If it's not going to be a gas, it'll tell you it's a liquid. Okay. All right, so this is not balanced, so I'm going to do a quick balancing here. First off, if you don't know what I'm doing, go back and review the balancing video. But I see 6 carbons, so I'm going to need 6 carbons. I always do my carbons first. Then we balance hydrogens. I see 12 hydrogens. I see 2 here. So I'm going to put a 6 in front of the hydrogen to give me 12. 6 times 2 is 12. Now, I need to add up all my oxygens on my reactant side. I have 6, I have 2, so 6 times 2 is 12 oxygens. And then I have 6 times this 1, so I have 6. So I have 18 oxygens in total on the reactant side. And then over on that's my product side. So I have 18 there. And then on my product side, I have 6. And I am going to need, to get to 18, I'm going to need 12 more. So this needs to become 12. So I'm going to put a 6 in front. So 6 times 2 gives me 12, plus another 6 gives me 18. So now we're at 18. If you have no idea what I did, go back and watch that balancing video, because that's step number 1. You got to be able to balance the formula of combustion. All right, now into Hess's law. Let's go into Hess's law. I'm going to try and pick another color here. There we go. And I'm also going to grab this chart up here. We're going to need this. This is from our data booklet on page 5. These have all the heats of reactions. Ooh, I need to get rid of. Oh. All right, let's get going again. I just moved my data booklet table. This is from page 5. I would have that open so you can find these as we go. So we are trying to find the enthalpy of reaction, or the heat of our reaction. And we're first going to start looking at the products. So we need to look at the heats of formation of each of the products times the number of moles that we have for each product. So we're going to start here. I'm going to look here and where I'm drawing a star. We're going to start with carbon dioxide. I'm going to look up carbon dioxide in my formula table. Here we go. Carbon dioxide. There you are. And it has a heat of formation of negative 393.5. You do need to keep the negative. So this is where it gets a little messy. All right. And we also have to look at, I'll do the 393.5, and it's kilojoules per mole. Now, there's also this little n here, remember? That n's how many moles. So let's look at our balanced formula, and this is why we need a balanced formula, and there are 6. So we've got 6 moles here. Whoops. 6 moles. Alrighty. Then we have to add all our products together, because we've told we need the sum of all of our products. So we're going to look at product number 2 here, and that's the water, and it's in gas form. So we're going to go find water, and there it is. There's water. There's 2 waters. Make sure you pick the one that's a gas. All right. And there is our enthalpy heat of formation, negative 241.8 kilojoules per mole. And how many moles are there of water? There are 6. Okay, so I'm going to put all that in a big bracket because we have to do all that first before we do the next half of the reactants half. So we're going to make sure we figure out the product's value and then the reactants value and then subtract them after we've gotten both. So here we go for the reactants. We are going to look at our reactants. So here we have got glucose. We were told that was what that was in the question. So here is glucose. Look at its heat of formation. Ooh, it's big. And there's only one glucose, so it's going to be 1 times negative 1273.3 kilojoules per mole plus oxygen. Look up oxygen. Oh, you're not going to find oxygen. Remember oxygen, element. We talked about that on the last slide. All elements have a heat of formation of 0. So we're going to be, there's 6 of them, but each of them have a heat of formation of 0. So it's just going to end up being 0, which is lovely. It makes our calculation just a little bit easier because we've got oxygen in every combustion reaction. All right, so let's do a little bit of math here. How does this all pan out? So we're going to go 6 times 393, and don't forget the negative sign. Okay, interesting. I'm just noticing that in the answer key, it's wrong, so I'm going to have to change that. So it's going to be 6 times 393.5, which gives you 2,361. And you notice I just have kilojoules now. It's because the moles cancel each other out when we multiply these two numbers together. We still do have a negative symbol, though. Then we are going to add this next number, which looks like it's going to be a negative number. So I'm going to pause and get that number. All right, so 6 times negative 241.8 gives us negative 1450.8 kilojoules. All right, and that we need to make sure we do this calculation here before we subtract our reactants. We just got 1 times this number here, so we've got negative, don't forget the negative there, and then it's times -1, so negative 1273.3 kilojoules, because we went 1 times there, so we have no moles left. And then this is just plus 0, 6 times 0, 0, so we'll just leave it at that. All right, do the calculation and see what we all get. All right, so I took my first number, negative 2,361, and I added it to negative 1,450.8, and I get a negative 3,811.8 here. And then we have minus negative 1,273, and we get, all right, so we subtract our two numbers, keeping in mind one's negative. So we end up with negative 2,538.5 kilojoules. If you are not getting this on your calculator, make sure you go back and try or get help if it's not working out for you. All right, moving on. I'm going to do another practice problem because I know these look very intimidating, but and can get messy as well. So we just need to make sure we're keeping everything really organized when we're doing this question. So this question, we actually already have a balanced equation. So that's lovely. That saves us a bit of time. A lot of times you will be getting a balanced equation. It just depends. You never know. So you need to be able to come up with the balanced equation. Anyway, calculate the heat of reaction from the combustion of butane gas. All right, so we've got our balanced equation for butane. Remember, butane had 4 carbons in it. It's a 4-carbon chain. All right, so we're going to get our equation. Let's write out our equations from page 5 in our data booklet. So, delta F, R. Oh, just a second. Let's try that again. Delta RH is equal to the sum of the moles of the heats of formation of our products minus the sum of the moles times the heats of formation of our reactants. Alrighty, so let's look at our products. So here's our two products. We've got carbon dioxide and we've got water, and they're both in the gas state. So our numbers are going to look very similar to the last one. So we're going to have all our products in brackets. We're going to have 4. I'm going to start with the carbon dioxide. 4 times, I'm just going to leave out the units to make it a little bit easier. 4 times the heat of formation for carbon dioxide, which I'm going to find on the table right now. So look for it on your table as well. And you should see negative 393.5 kilojoules per mole. I'm just leaving things out. And we're doing the sum of them, so we need to add that to the next product, which is water. And there are 5 moles of water. And we're talking water vapor, so go find water gas. This molar heat of formation is 241.8 kilojoules per mole. All right, so those are both of our reactants, and now our products. Oh my gosh, products. Those are our products, and we're going to subtract the molar heats of reaction of our reactants. So we're going to look up butane. And if you find butane on your chart, you will see, well, first off, we only have 1 mole of it. So it's 1 times negative 125.7 kilojoules per mole. And we are going to add our reactants together. The other reactant is oxygen, which we now know is just 0 heat of formation. So it doesn't matter if we have this fraction of 13/2 moles in front of oxygen. It's just going to be 0 for the heat of formation because it's an element. All right, let's do some math. I'm going to pause for a second while I do the math, and you pause and do some math here. All right, So 4 times negative 393.5 gives us 1,574 negative. And then we're going to add that to 5 times negative 241.8, which gives us negative 1,209. Then we're going to subtract, because we need to subtract all of our reactance values over here. 1 times negative 125.7 is just negative 125.7. And then the oxygen term becomes 0, so we can ignore it. So these are our values here, and let's get our final enthalpy. All right, so if we do the math correct, we get negative 2,657.3, and our units are kilojoules. So our units for energy and enthalpy is kilojoules, so our final answer is 2,657.3 kilojoules. And something I did not remember to mention before, if your answer is negative, that means energy is released, and it's therefore an exothermic reaction. Okay, so that's the amount of energy. If you were to burn 1 mole of methane, this is how much energy you're going to burn and release. This is how much energy you're going to get when you burn 1 mole of this butane gas here. Okay. If there was a 2 in front of there, you could probably guess what's going to happen, but you're going to get double the amount of energy released if you have double the amount of moles of butane burning. And I believe that's the next question. Yes. So here we have a diploma question here. Here we have that same formula. Looks very similar. It's just balanced differently. So we have butane gas. We've got 2 moles of it. So everything's been doubled. So instead of that 13 over 2 fraction, we have just 13. Everything else is doubled. So they're asking the energy released when butane burns. So we need to actually keep in mind that there's 2 moles of butane there. So when we do out our equation and our products go in, no problem, right? We've got the 8 in front of the carbon dioxide, 8 moles of carbon dioxide. There's our molar heat for CO2. And then here's our 10 for the water when we're looking at the products. And there's our water vapors, molar heat of formation. So these should look familiar to you. And we're subtracting our reactants now. Here was our butane coming in. There's our butane's molar heat of formation. And look, here's the 2. The 2 is also here for butane. So got to watch that. And then we have our 13 moles of oxygen. And of course, oxygen's molar heat of formation is just 0. So it gets canceled out. Try this on your calculator. Make sure you get this answer here. But you'll notice this is twice the amount of energy as the last question where we only had 1 mole of butane in our formula. So make note of that. So it'll just depend on how the formula is balanced. All right, we went over coal-fired generation in the last lesson, so I'm not going to repeat myself. Go back and watch that video if you want, but this is a review, making sure that you understand how this is happening. Coal-fired plants, again, same kind of idea. This is kind of looking at the advantages and disadvantages, and we're going to be drawing this into an assignment in the second chapter, but this you might find useful here just to make sure you understand. What are the advantages of using coal? It is cheap and affordable. It's abundant, especially in Alberta right now. There's a lot of it. Not forever, of course, because it is non-renewable, right? It's reliable, it's got high energy yields, and we can get a lot of energy out of there. It can be made cleaner by removing the carbon. If we capture the carbon dioxide, that should be dioxide. If we remove the carbon dioxide, if we capture it, or we remove the sulfur, that can make the coal cleaner. Unfortunately, it's a non-renewable resource, so it does have a limit to how much there is on Earth. It also produces sulfur dioxide, carbon dioxides, sulfur monoxides, which we know cause acid rain. Remember that from back when in chapter B. There are also can be some radioactive particles and mercury released as well. And we know it's going to cause environmental destruction as you're not only mining that coal, but also as we release carbon dioxide, we are getting that greenhouse effect that is being caused. Okay. So I threw in a couple extra charts at the end here just for you to practice reading your charts. What does this chart tell you? When I read this chart, I am looking, okay, I see coal consumption for 2019. Keep in mind that's 3 years ago from the time I'm making this video. I am seeing that Canada is there and there's its colors. So our coal consumption is not super high compared to places like China or the United States, but I also noticed that this is not per capita, right? So this is going to be total based on how big that, how much is used in the country. And I also know that China and India are like way huger populations than Canada, same with the US. So the fact that Canada even registers is quite interesting. So we're using a lot of coal is what I'm looking at here. Okay. What does this chart tell us? This is, okay, so this is the share of electricity produced by source in the world. Okay, so I'm looking at coal. Coal in 1985 was about 30, let's say 38% ish of the electricity produced in the world used coal. And it looks like in 2020, it's down below that 35 line. So I'd say that's about a 34%, it's roughly, or 33.5. So it's reduced, it's going down in the amount that coal is used to produce electricity around the world. However, I can see a trend here with the gas. So I'm going to assume this is natural gas. And I can see that it's trending upwards. And that's similar to what we're seeing in Alberta, right? Our coal usage is going down for electricity, but our natural gas use is going up. It looks like hydropower is pretty consistent or gone down a little bit. Yeah, it's gone from 20% down to about 16 or 17. Nuclear has definitely gone down. It looks like it started at 15% in 85, gone up a bit, and then now it's down to 10, which is interesting. We will be talking about nuclear next. You can see oil has steadily been going down, but wind has been increasing. So that's great to see. This is a renewable resource, which we're going to also be talking about. And solar has been increasing too. Now, keep in mind, this is across the world and only over since 1985 to 2020. So that's how I would read that chart and talk about what I see there. What does this chart tell me about the coal use in Canada? All right, so here we go. Just Canada. We're looking at what sources are being used to produce electricity. So we're not just talking about energy, we're focused on electricity. Looks like hydropower has remained pretty consistent across the years. Nuclear looks pretty consistent still, like started around the 11-12%, and I'd say it's still around the 12 or 13% range. This line's gone down though. What is this line? This is coal. There we go. So coal has been being reduced in Canada as well for electricity. So we were up in the 18% range, I would say, 17, 18, and now we're under 10, so around the 8% mark here we come across. Yeah. We can see that wind has increased, taken a portion of the amount of energy, electricity that's produced by wind has gone up. Solar looks pretty steady. It's gone up a little bit, like 1% or so. Anyway, so that's what I can get from those charts. And these are the kind of processes I want you to go through in your head when you're looking at these charts, because you will see some of these on your quizzes, I'm sure. All right, and these are the references used, and I thank them for letting me use them.